From above, we see that in case of a all-path system, poles and zeros form conjugate reciprocal pairs. Now, let us look into another case of LTI systems, that is magnitude transfer function. If h of z is a LTI system, then the function c of z is equal to h of z multiplied by h star of 1 by z is called magnitude transfer function. From this we can say that any c of z which can be written into this form is called magnitude transfer function. From magnitude transfer function we can conclude that poles of the magnitude transfer function, that is p1 and p2, form conjugate reciprocal pairs, and zeros of magnitude transfer function form conjugate reciprocal pairs. So if there is a pole located at A, then there is another pole located at 1 by A star. Similarly, if there is a pole located at B, sorry, there is a zero located at B, then there is another zero located at 1 by B star. For example, the system h of z is equal to 1 minus 2z inverse multiplied by 1 minus half z inverse divided by 1 minus 3z inverse multiplied by 1 minus 1 by 3z inverse is magnitude transfer function, as the zeros are 2 comma 1 by 2, which is a conjugate reciprocal pair, and poles are 3 comma 1 by 3, which is also a conjugate reciprocal pair. Now let us consider another case which we need to cover as related to LTI system, that is inverse system. Let us consider a LTI system with system function h of z and ROC R. Then the inverse system g of z is defined such that h of z multiplied by g of z is equal to 1, and ROC of g of z should be chosen such that it overlaps with R from the possible ROCs of g of z. That is, from the given g of z, find the possible ROCs, and out of these choose RG such that it overlaps with R. Now let us consider a example in which it is given that there is a LTI system h of z is equal to 1 minus 2z inverse divided by 1 minus 1 by 3 z inverse with ROC as mod z greater than 1 by 3. Now we need to find the inverse system of the h of z. The inverse system of h of z is defined as hi of z is equal to 1 minus 1 by 3 z inverse divided by 1 minus 2 z inverse. This is obtained as 1 by h of z. But from hi of z we see that the possible ROCs are mod z greater than 2 and mod z less than 2. Now we need to find the ROC of hi of z out of these two ROCs. We see that here the ROC mod z greater than 1 by 3 overlaps with mod z greater than 2, but it doesn't overlap with mod z less than 2. From this we can say that the ROC overlaps with mod z, here we see that the ROC mod z greater than 1 by 3 overlaps with mod z greater than 2 completely, and it doesn't overlap with mod z less than 2 completely. So from this we can say that the ROC of inverse system is given as mod z greater than 2. Now let us consider another example as per which there is a LTI system of system function 1 minus half z inverse divided by 1 minus 2 z inverse. It is given that this system is causal. Now we need to find the impulse response of inverse system. Here we see that as h of z is causal, the ROC of h of z is mod z greater than 2. From this we can say the system function of inverse system hi of z is defined as 1 by h of z. This is equal to 1 minus 2z inverse divided by 1 minus half z inverse. But here we see that the ROCs possible for hi of z are mod z greater than half and mod z less than half. Here we see that the ROC mod z greater than 2 overlaps with mod z greater than half completely. So this is a possible ROC, whereas mod z less than 1 by 2 is not a possible ROC as it doesn't include any part of the ROC mod z greater than 2, that is of the original system. From this we see that the inverse system's transfer function is 1 minus 2z inverse divided by 1 minus half z inverse with ROC as mod z greater than half. From above we see that the inverse system can be simplified as 1 by 1 minus half z inverse minus 2 multiplied by z inverse divided by 1 minus half z inverse, and the corresponding ROC is mod z greater than half. From this we can say that for the first part, that is 1 minus half z inverse, the inverse z transform is 1 by 2 whole power n u of n, and for the second part, that is z inverse of 1 by 1 minus half z inverse, the inverse z transform is 1 by 2 whole power n minus 1 u of n minus 1. From this we can write that the impulse response of the inverse system is hi of n is equal to 1 by 2 whole power n u of n minus 2 into 1 by 2 whole power n minus 1 u of n minus 1. This is the impulse response of the inverse system. Now let us consider some of the nodes as related to the systems that we discussed already. As per the first node, any stable and causal LTI system with system function h of z can be factored as a cascade connection of a minimum pass system, that is h min of z, and a all pass system, that is HAP of z. So let us look into the same with an example. Consider a system with system function as h of z is equal to 1 plus 3z inverse divided by 1 plus half z inverse. Let the ROC be mod z greater than half. From above we see that h of z can be factored as 1 plus half z inverse sorry h of z can be factored as 3 times 1 plus 1 by 3 z inverse divided by 1 plus half z inverse multiplied by 1 plus 3 z inverse divided by 1 plus 1 by 3 z inverse. Here we see that the system z inverse plus 1 by 3, that is the second part, divided by 1 plus 1 by 3 z inverse is all pass system, and the first part, that is 1 plus 1 by 3 z inverse divided by 1 plus half z inverse is minimum phase system. So here the given stable and causal h of z is split into two parts, of which the first part is a minimum phase system and the second part is a alpha system. We see that the second part is an alpha system because in this case the poles and zeros form conjugate reciprocal pair, that is 3 comma 1 by 3, sorry, minus 3 comma 1 by 3, and whereas in case of first part the poles and zeros are inside unit circle and it is a causal system from the given data. From this we see that any system function h of z can be factored into a can be factored as a cascade connection of a minimum phase system and all pass system. Now let us consider another note in which it is given that the group delay g of omega of a alpha system is non-negative for all values of omega. It means that it is greater than or equal to 0. Let us consider this by an example. Let there is an alpha system given as h of z is equal to z inverse minus 2 divided by 1 minus 2 z inverse. Upon substituting z is equal to e power j omega, we get that h of e power j omega is equal to cos omega minus 2 plus j sin omega, sorry, minus j sin omega divided by 1 minus 2 cos omega minus j, sorry, plus j 2 sin omega. From this we can say that the phase is given as tan inverse of sin omega divided by, sorry, minus sin omega divided by cos omega minus 2 minus tan inverse of 2 sin omega divided by 1 minus 2 cos omega. Here we got the phase of h of e power j omega as phase of the numerator minus phase of the denominator. From this we see that the group delay g is equal to minus d phi by d omega would be greater than g or equal to 0 if plotted. From this we can say that given any alpha system, the group delay would be greater than or equal to 0, that is it is non-negative. Now let us consider a problem as per which it is given that there is a system function h of z given as 1 minus 2 z inverse multiplied by 1 minus half z inverse. We have to find if the system is alpha system or linear phase system or minimum phase system or magnitude transfer function. For the given h of z, we see that the zeros are located at 2 comma 1 by 2, which form a conjugate reciprocal pair. From this we can say that the given system is a linear phase system as zeros form conjugate reciprocal pair. In case of alpha system, poles and zeros together form the conjugate reciprocal pair, which is not satisfied here. In case of minimum phase system, if the system is stable, poles and zeros should be sorry, if the system is causal, poles and zeros should be inside unit circle, which is not satisfied here. And in case of magnitude transfer function, zeros should form conjugate reciprocal pairs and poles should form conjugate reciprocal pairs individually. So this could be a magnitude transfer function as well. From this, we can say that the given h of z satisfies the requirements of satisfies the things related to a linear phase system and the magnitude transfer function as zeros form conjugate reciprocal pairs. Now Let us consider a problem as per which it is given that for a LTI system, the group delay plot is given as minus 2 omega plus 3. It is given that phase at omega is equal to 0 is equal to 0. From this information, we need to find phase of h of e power j omega for every omega of that LTI system. We know that the group delay can be expressed as g of omega is equal to minus d phi by d omega. From this, we can write that phi of omega is equal to minus omega square plus 3 omega, sorry, omega square minus 3 omega plus c. This is because if we obtain d phi minus d phi by d omega, that would be equal to minus 2 omega plus 3 from the obtained phi of omega. But it is given that phi of 0 is equal to 0. That is, phase of h of e power j0 is equal to 0. From this, we see that c is equal to 0. This is by substituting in the obtained phi of omega. Here c is a constant. From this, we can say that the phase of the LTI system can be given as phi of omega is equal to omega square minus 3 omega. This is for the given data and for the given LTI system. Now let us consider another problem as per which it is given that there are two signals x1 of n is equal to sine of omega 1 n plus phi and x2 of n is equal to sine of omega 2 n plus phi. It is given that x of n x1 of n is equal to x2 of n for every n and x1 of 0 is equal to 0 and x1 of 1 is equal to 1 by root 2. From this information, we need to find the value of omega 2 out of the options given, that is 13 pi by 4, 5 pi by 4, 7 pi by 4 and 9 pi by 4. For the given x1 of n, if we substitute n is equal to 0, we see that x1 of 0 is equal to 0 is equal to sine phi. That implies phi is equal to 0. Similarly, if we substitute 1, we see that x1 of 1 is equal to 1 by root 2 is equal to sine omega 1. From this, we see that omega 1 is equal to pi by 4. So from the obtained pi and omega, we can write that x1 of n is equal to sine of pi by 4 n. But it is already given that x2 of n is equal to sine omega 2 n is equal to sine of pi by 4 n. From this, we can say that omega 2 is equal to pi by 4 plus 2 pi k, where k belongs to z. Say if k is equal to 1, then we can write that omega 2 is equal to 9 pi by 4. From this, we see that out of the given options, the option D, which is 9 by 4, could be the value of omega 2. If x1 of n is equal to x2 of n and from the given data. Now, let us consider another problem as per which there are 4 LCCDEs given in the options A, B, C and D. We have to find which of the options corresponds to FIR filter and Which of the options corresponds to IIR filter? The option A has y of n is equal to y of n minus 1 plus x of n. Option B has y of n is equal to x of n plus y of n minus 2. Option C has y of n is equal to x of n minus 1 by 2 x of n minus 1. And option D has y of n is equal to sigma m equal to 1 to infinity x of n minus 1. In case of option A, we see that the output at any instant depends on the output at other instants and the past input. So we can say that it is an IIR filter. And in case of option B, also the same applies. So option B is also an IIR filter. In case of option C, we see that the output at any instant depends on the input only. So it is an FIR filter. Similarly, in case of option D, we see that the output at any instant depends on input only. So this is also an FIR filter. So from the nature of the LCCDE, depending on the case that if the output depends on the input only, or if the output depends on the input and output at other instants, we can classify the filter as FIR or IIR. Now let us consider another problem as per which there is a LTI system of system function h of z is equal to z inverse minus 3 phase 10 degrees divided by 1 minus pz inverse. There are four options given as related to this LTI system. As per option A, the system is all pass if P is equal to 3 phase minus 10 degrees. As per option B, if P is equal to 2 phase 30 degrees, then the system is stable and anti-causal. As per option C, if P is equal to as per option B, if P is equal to 2 phase 30 and the system is stable, that implies the system is anti-causal. As per option C, if P is equal to 1 by 4 phase minus 30 degrees and unstable, that implies system is causal. We have to pick if these if any of these three options are correct. Now let us consider option A. As per option A, we see that the system is all pass. If the system is all pass, the poles and zero should form conjugate reciprocal pairs. We see that the 0 is located at 1 by 3 phase 10 degrees. So pole should be located at 1 by 0 conjugate. That implies P is equal to 1 by 1 by 3 phase 10 conjugate. This is this leads to P is equal to 3 phase minus 10 degrees. So from this we can say that if the system is all pass, pole is located at 3 phase minus 10 degrees. So the option A is correct. Now let us consider option B, as per which if P is equal to 2 phase 30 degrees and system is stable, the possible ROCs are mod z greater than 2 and mod z less than 2 for the given system. As the system is stable, the ROC should include unit circle. So mod z less than 2 is the possible mod z less than 2 is the correct ROC and mod z greater than 2 is not a correct ROC. From this we see that if P is equal to 2 phase 30 degrees and the system is stable, then mod z less than 2 is the correct ROC. From this we see that the system is anti-causal as ROC is inside a unit circle. From this we see that the option B is also correct. Now let us consider option C, as per which P is equal to 1 by 4 phase minus 30 degrees and system is unstable. The possible ROCs are mod z greater than 1 by 4 and mod z less than 1 by 4. Yes, the system is unstable. ROC shouldn't include unit circle. From this, we can say that mod z greater than 1 by 4 is the ROC of the system, and mod z greater than 1 by 4 is not the correct ROC as it includes unit circle. As mod z is less than 1 by 4, we see that the system is anti-causal and hence non-causal. So from this we can say that if P is equal to 1 by 4 phase minus 30 degrees and system is unstable, the system would be non-causal. From this we can say that the statement C or option C is not correct. From this we can say that from the given data, the options A and B are correct and option C is not correct. Now let us consider another problem as per which the system function of a LTI system is given as h of z is equal to z inverse minus 2 phase 30 degrees divided by 1 minus 2 phase minus 30 z inverse multiplied by z inverse minus 2 phase minus 30 degrees divided by 1 minus 2 phase 30 degrees z inverse. From this system function given, we have to find if the system is all pass or linear phase or magnitude transfer function or minimum phase. From the given data, we see that the zeros are located at 1 by 2 phase 30 degrees and 1 by 2 phase minus 30 degrees and poles are located at 2 phase minus 30 degrees and 2 phase 30 degrees. From the obtained zeros and poles, we see that there are two sets of conjugate reciprocal pairs of poles and zeros. From this, we can say that the given system is all pass system as poles and zeros of given system form conjugate reciprocal pairs as shown. We can say that the given system is all pass system.